Please grab some food too. Look at how much we have.
Should I give a minute for people to grab some food first? So. Very good. All right. Well, I appreciate the introduction to both how LLMs work and some concrete real-world applications. This is going to be, well, a philosophy talk, so a little bit different perspective. But all right, so to kind of dig in, basically the talk is going to give kind of three phases, a little bit about large language models, which might be lost, might be, you know, something that this audience already knows, so maybe a review. I'm not sure what all background various people come from, but I was told this was open to the public, you know, any undergrad talk, so I wanted to make sure we had some background on the table. Then some stuff on this philosophical concept we call emergence, that originally developed in context that had nothing to do with large language models or computing, and then something to do with how those two ideas fit together. All right, so starting with large language models. So this is actually just a prompt that I ran just 3 times, once on each model. So if you run it at different times, you get slightly different results. But just for those of you who don't spend all day playing around with these, as I do, and the folks in the front row absolutely do, maybe you're not familiar with how much of a change we've had in just a couple of years. So ChatGPT 4, right, is less than a year old in terms of public use. ChatGPT 3, just a year before that. Before that, we're talking about ChatGPT 2. Now let's see what a long way we've come. So ChatGPT, well, not like ChatGPT 2, GPT 2. You know, I just type that in and I have it autocomplete. And for GPT-2, we get kind of word salad. Like this is like an English sentence of some kind, but I don't think it means anything really. Large language models work by providing a textual set of variables for each language in your model. Yeah, I mean, it knows how to generate an English sentence, but I don't think this is like, I mean, I'm not a computer scientist. Maybe I'm missing something, but I really don't think that's telling us any kind of content answer to the prompt. It's just kind of plausible sounding words that might kind of follow this. It's sort of computer science ease. The way that, you know, sometimes maybe someone who's just starting to read a philosophy text might, you know, write a paper that uses some words in the text, but not in a way that really, you know, fits with anything. Then, you know, we get GPT-3. So GPT-3 clearly gives us a real answer to this question. The combination of machine learning and natural language processing techniques, simplified overview, and I just took out the numeric heading, so it gives you like a little sentence or two under each one of these to more fully explain. But I stripped those out just for the sake of playing. So, you know, it gives you there's these different aspects to how they work. So we went from just kind of already in advance of like, hey, we can actually write an English sentence with proper grammar, which we couldn't necessarily do before that, to an arbitrary prompt. Now to, no, I'm really answering your question, but in a way that might be, in this case, a little bit insensitive to context. So I've asked a question that clearly indicates that I'm not an expert, right? An expert wouldn't ask, how do large language models work? They would ask some more specific question. And yet the answer it gives me is kind of in terms of technical concepts like machine learning, natural language processing, tokenization and coding. So it's using kind of comp sci context, which concepts are correct, but a little bit insensitive to the kind of the tone or the context of the question, right? And now ChatGPT 4, you see how the jargon is much reduced, right? So now we don't say, you know, these jargon terms, we just say analyzing vast amounts of text data to learn patterns and instructions and patterns and structures, and we use much less. These are basically the same answer as this because, well, it's the same fact, and they both sort of, you know the fact and can tell you to it, but it's much less jargon. So now we have a system that is really responding to the tone or the context of the prompt, right? Which is, again, this prompt is clearly not being asked by, you know, a comp sci professor or something. So we've come a long way in just a couple of years. And it's interesting that this progress, these three vastly different, you know, answers, so especially the first two, right? Vastly different. We go from complete word salad to like a solid answer to our question, are really done by the same structure. It was originally GPT's Transformers paper, which came out, or sorry, Google's Transformers paper, which came out in 2017. It's originally supposed to do language translation, was the original context. So I want to, Google Translate's been out for a while, it predates this. They were trying to improve Google Translate with the structure. And I'm not going to go into the structure because I think the people who do computer science already know it. People who don't do computer science aren't going to learn it in 2 minutes. But the important thing is this structure was originally developed for language translation, and it really is unchanged since 2017. So the 3 vastly different responses that we saw on the last slide are all generated by a program that has the exact same structure to it. It works in the same way at the underlying system. So we might think, well, what's that about, or how does that work? And the answer is basically that we've kind of fed more data in. So I'm kind of moving back and forth between different modalities. I'll talk about large language models, but this is an image model. And basically what that transformer structure does is take a bunch of data in. So in this case, a bunch of faces. It's trying to maybe identify or categorize those faces in this case. And it carves those faces up into features, but they're to us, they're kind of black boxes because these features don't really correspond to any way that we would describe faces. It's not like, oh, it's all the lips and all the ears. Like it carves things in ways that seem very perhaps strange to us in terms of how it might understand faces or features, and then eventually comes up with some similarity mechanism among the faces we give an output. So those of you who are on Facebook, you might remember a few years ago the big deal about Facebook auto-tagging your friends. If you'd been tagging friends in pictures, Facebook would auto-suggest, oh, this is Joe again. How did it do that? Well, this is how. I say a black box because we don't really, in a way, know what these internal bits of the state kind of represent. They represent kind of funny things that don't really correspond to any concept we have. But when you get a lot of them working together, you get these kind of cool, powerful results that we're seeing. And so we might think of this as kind of, in a more general context of software, as a level of abstraction, right? So on the bottom, we've got physics, right? So you've got some voltages, leading to some other voltages later on in a piece of silicon, a semiconductor, right? So, computers run on physics, obviously. We can abstract those according to a logic diagram, as resistors, and then a logic diagram. Eventually up here, we're writing what we call software or code, and building applications like this lovely application for analyzing 311 data. And we can think of it as a kind of increasing level of abstraction. Right down here, we've got the nitty-gritty of a bunch of physics, and up here we have some really high-level idea, like I want a narrative that comes out of this 311 data. So we have more complexity down here, right? The physics that's going on to execute one of her queries is wildly complicated. Like there's, billions and billions of transistors, engaging how many operations. But the idea that you can summarize it is very simple. What's the leading cause of 301 complaints, in the Bronx over the last year, or whatever you want to say. All right, so we have this different kind of levels of abstraction that are going on. And just to give a particular kind of example of that, so just at the level of and you push down both of these buttons, the light comes on. If you push only one button or neither button, the light is off. So logically, for any of you who are computer scientists or philosophers, you should recognize the and operation, right? Only if I put in two of the, of the same thing, do I get the right thing out. Well, this is actually an and, so this is not and. So sorry, that's just up. So if I put in, so it's not and. If I put in 2 on, then I get 1 off, right? But okay, so we can see that there's a lot of physics going on here, right? There's resistors, there's transistors, there's various physical elements, and we can represent those schematically at a very high level, right? With just a truth table. So we have a different level of abstraction here, right? Here, you know, a transistor has an allowable input voltage and output voltage. So there's a certain voltage at which maybe it might come on or might not, because we're not, you know, it's not rated to that, but you have to be clear of a certain voltage. So say if it's, you know, over a certain voltage, it'll definitely be on. It's below a certain voltage, it's definitely off. And in the middle, there's a bit of, you know, fuzziness, what will happen perhaps. But as long as we can regulate it such that it's usually way under or way over, we can represent it, you know, in this kind of digital way as being, you know, one outcome or the other. And we can kind of abstract from the various details of exactly what our activation thresholds are and that kind of stuff, and just say, boom, this is, you know, the schema that we have. So we have a higher level of abstraction. So this is kind of at the very bottom of the stack, going from physics, you know, to a representation of a logic gate. But we do the same thing the whole way up the stack, right? We kind of just we take things that are messy processes at a lower level, and we give them some kind of abstract organization. So again, at the same level, at a higher level, we go from, you know, a whole bunch of messiness of 46 million rows in a 311 database to a simple narrative of, you know, what's going on in your zip code, right? So again, a higher level of abstraction. And that's what software does, is kind of abstracts. So particularly, I want to draw attention to kind of one issue in the way we think of large language models as being abstract. So this is abstract physics of some bits of an NVIDIA graphics chip, which is what these large language models actually run on. But this is already not quite at the physics level. It's already a little bit abstracted from where we were. But you know, it's super complicated, right? And this is just a tiny little chunk. Like, these things are wildly complicated. They have billions and trillions of transistors in the whole system. So if we ask, how did we get from a certain input to a certain output? We can answer that at a kind of a physical or logic board level of like tracing. We start with certain pins on and certain pins off at our initial state. And then we trace it all the way through to other pins on or off, which make certain things appear on your screen. Because at the end of the day, your screen is just certain bits being lit and certain bits being unlit, right? Or lit a certain color. But we can also understand this as occurring kind of in the space of reasons. If I ask, why is this the output of my question, I can say, well, because that's actually how they work, right? I can say, because it's the right answer. Like, why is this what the LLM's telling me? Well, it's because it's the answer to my question. In the same way that if I ask you, like, why did you give me that answer today? You can say, well, I was trying to be helpful. You asked me the question, so I told you the truth, or at least as well as I understood it, right? Like, you don't tell me in terms of, you know, your neurochemical firings why you answered the question a certain way, right? You answer in the space of reasons. Like, why did it happen? Well, because these are the reasons I had for answering you, or this is the data sources that I have, or something like that. So you answer this much higher level of abstraction. So we can see kind of two different answers about how they work. One at this very low level of abstraction, perhaps all the way down to physics, and one at a very high level of abstraction of, well, we're asking and answering questions. And this is, in a way, what makes me say something like the word hallucination, right? If I say an LLM hallucinates, what I mean is, I asked it a question and it gave me the wrong answer, or it gave me a silly answer. But that kind of implies that its words mean something. If the words mean something, then I can say, well, they mean something false, right? But if I answer at a purely physical level, that's a kind of a nonsense thing, right? Some pins lit up over here on this board, and some pins lit up over here on this board, and it's the laws of physics that connected the input pins to the output pins. And I can't really say, oh, those are wrong. Like, what do you mean they're wrong? Like, they're just the pins that light up on the outside when you light up the certain ones on the inside. There's no right or wrong for that. It's just physics. So we kind of have to move up to a high level of abstraction, this question of the space of reasons, we might say, in order to say things like, well, there was a hallucination, or the answer to my prompt wasn't very good, or something like that. So I want to suggest that this is reminiscent, this idea of having explanations at two different levels that work differently is not a problem that we first encounter with large language models. It's a problem we've been dealing with in a long time, for a long time, in the, of course, way of understanding other sciences. So this is just an XKCD comic, but you know, the idea is that from a certain perspective, we might think of higher sciences as just applied versus the lower science, right? So if you want to know how chemistry really works, they'll say, well, there's a lot of quantum physics involved. There's the whole quantum chemistry field, which tries to relate chemistry to physics, say why chemistry happens in terms of physics. If you ask why biology works a certain way, they'll often point you to biochemical mechanisms, right? They'll say, well, DNA replicates that way because of this, this enzyme that's catalyzing it or whatever. They'll give you these chemical answers. If you want to know why psychology happens in a certain way, they'll give you biological answers, right? This is all the serotonin and neurotransmitter stuff we hear all the time, right? Just in a common sense way now. It's entered regular everyday talk. And if you want to know why, societies act in a certain way, people will answer in terms of, individuals' interests or whatever. So we might think these are just kind of more and more applied, and, all the way down to math at the end. But there's an interesting question because, of course, these sciences still exist. We haven't gotten rid of these departments just because they're applied, right? Like, if you have a chemical question, you don't call a physicist, you call a chemist. If you have a biological question, you don't call a chemist, you call a biologist. Why? Well, somehow these answers are supposed to be like more powerful or effective or enlightening or explanatory than these answers. So there's answers at two different levels, but they don't work the same way. What's going on there? And how do we make sense of it? Well, that's the question of emergence, something that philosophers are worried about. So this is just the same kind of idea, but done as a pyramid. So each one kind of, Jessica Wilson defines emergence as the coupling of cotemporal material dependence. So what happens chemically depends on what happens physically, where the electrons and stuff are actually moving will determine what happens chemically, where how the chemicals interact in terms of what happens biologically, et cetera. But while there's material dependence, well, the things up here depend on what's going on down here. There's also a kind of ontological and causal autonomy that somehow the laws of what are going on up here aren't simply reducible to the laws down here. These sciences are still doing work for us. What does that look like, or what? Let's give an example. So physically, right, we can draw all of the possible standard model interactions. So these are all the things that particles can do to each other. Complete list. And then, of course, in chemistry, right, if you all remember, your last chemistry class, perhaps vaguely remember doing stoichiometry, right, showing certain interactions as happening. And at some level, we might think, well, that's just various physical goings on, right? It's just electrons, going from here to here, emitting this photon, coupling to this, whatever. But of course, by Avogadro's number, we know that 1 mole of these substances has spectacular numbers of particles going on. And in practice, nobody can predict just from physics what else is going to happen chemically. So chemicals, we think when two chemicals react, that somehow it is just a physical process. It is just some combination of this. But these stoichiometric laws of chemistry summarize a massive amount of physics going on, and the physics doesn't really let us predict the chemistry, at least not in detail. Okay, so Jessica Wilson introduces two kinds of emergence to think about. One is weak, one is strong. So weak emergence is where the higher level we can deduce, we can deduce it in principle. Like if we knew all the physical facts and we had like a perfect mind, perfect knowledge of physics, we could predict all the chemical results, but we just in practice it's too complicated. Whereas with strong emergence, where even in principle you couldn't do that. We can talk about it in terms of powers that in weak emergence, the higher level lets us somehow summarize things in a simpler way, but there's nothing kind of genuinely new happening. Whereas in strong emergence, we have something totally new happening, some totally new power that we're observing. And that for weak emergence to work, we have to deny non-overdetermination. For strong emergence, we need to deny physical causal closure. Let me tell you about what those things mean, because that's some philosophy jargon. So she wants to introduce a hexalemma, which means you have 6 principles, but you can't hold all of them at the same time. The first principle is dependence, that higher level features depend on lower level features, right? That we're not just dualists. Like, if the higher level feature is happening, it's because something's happening at the lower level. Then 3 more: reality, efficacy, and distinctness, which are technically distinct but often go together. So reality, there's something real happening at both levels, like chemistry is real, physics is real, you know, we're not getting rid of anything. Efficacy, that you have real causal relations at both levels. There are physical causes, there are chemical causes, you know, we can speak genuinely about causality at all levels. And distinctness, that somehow we're not just redescribing what's happening at both levels, we're giving some kind of genuinely different, you know, explanation or describing something different. Then we have physical causal closure, which is the idea that physical causes don't depend on, or physical effects don't depend on anything but physical causes, that physics is kind of complete. And last, non-overdetermination. So the idea is that generally, you know, things just have kind of one cause, or at least one sufficient cause in the same way. There are some exceptions. We call the double rock throw. 2 people throw a rock at the window at the same time. Either rock would be enough to break the window, but then in general, life doesn't work like that. In general, we can say events kind of have one cause. And the argument she gives is that these are all plausible, but we have to give up at least one of them. Well, how does that work? Well, so the idea is, so we take P star, that's some physical effect, and then we pick P is whatever is the physical cause of P star. So by physical causal closure, it has some physical cause, call that P. Then we say, okay, S is whatever special science situation depends on P. S star is whatever special science situation, whatever high level situation depends on P star. So this is supposed to be causally efficacious too. So S causes S star. This is supposed to be real. It's supposed to be distinct. So it's not S and P aren't the same. S star and P star aren't the same. But now it sure looks like P doesn't just cause P star, it also causes S star. Why? Well, P causes P star, but S star depends on P star. So if I change P, thereby changing P star, well, I would also change S star. So it seems like S star has been kind of caused twice. Once by S, it's caused within the special science, but once by P, it's caused at the physical level. So somehow we've got 6 principles and we had to give up 1. So this leaves us kind of with 6 options depending on what we want to give up. If we give up dependence, we just have dualism. If we give up realism, then we have eliminativism. We just got rid of one level. We deny efficacy, we get epiphenomenalism. Top level doesn't really do anything, it's just a description. If we deny distinctness, then we get reductive physicalism. So we got 2 descriptions, but they're really the same stuff. They reduce the same thing. We deny physical causal closure. So we say it's not true that every physical effect is a physical cause, then we have strong emergentism. But if we deny non-overdetermination, we say that there can be 2 causes that are both real causes, then we have non-reductive physicalism. So I kind of want to look at where the AI kind of emergence falls in this camp, and I'm going to argue that AI is what we would call weakly emergent. Why? Well, okay. So to kind of review where we were about the two layers of description here. So this, we're not even close to the physical level here, but we'll describe, but this is the transformer level or the software level of how we might describe the AI, right? So there's an input node, and then it goes through many mid-level transformations according to the way that Google's transformer paper describes, and then we get an output. And so if we ask how do we get from the input to the output, well, we have to describe all the relevant transformers that it went through and how they all worked at the software level. But we also might just say this AI is a face classifier, we gave it a face, and the output layer is Mark. You know, it just says identify that face as Mark. Tag that as Mark. You know, on your Facebook. And if I ask, well, why is the output Mark? I can give two levels of description, right? I can give one level of description that's super complicated in terms of all the transformers, or I can give one level that's super simple and intuitive. Well, because that's Mark's face, right? Like, I know Mark. I'm looking at Mark right now. That's Mark. So the reason it output the word Mark is because that's Mark's face. So I'm kind of in the space of reasons, right? And I would say that this is wrong, just in case that's not Mark, right? So I'm giving this question of reasons and wrongness that's not available at this layer where it's just a talk about transformers. So we said that for weak emergence, we need to have somehow the simplification of something complicated. Let's talk about just how complicated GPT-2 is. So when we talk about transformers, you know, these diagrams always just give you a couple of parameters. But even GPT-2, that was the stupid one, right? That just could write English sentences that don't mean anything. 1.5 billion parameters. We call these the layers. So this is 3 layers, or 5, because it's input and output, so 5 layers. And we had, you know, what, 11 parameters. GPT-2 had 1.5 billion parameters across 12 layers. 10 billion training tokens. Tokens are kind of like words. They're like the words in its training database. And 10 to the 21st clock, the training compute, which is about how much all the world's computers do in 1 second. So you could train GPT-2 in every computer in the world in 1 second, basically, is how much training, you know, computation that's up. GPT-3, so that's the one that's giving us, you know, pretty functional answers to basic questions. 175 billion parameters across 96 layers. It's using it knows 50,000 kind of words, so to speak. The basic context available, there's different versions and a different context, but let's say basically it remembers the last 2,000 words that you've used. So that's the kind of problem she was talking about, you know, if you ask somebody something they don't remember, then they can't answer your question, right? Well, if it has a memory of the last 2,000 words, then if you try to refer to something back before that, it's just going to not remember. So it kind of limits the use of this. Trained on 300 billion tokens of data and 100 times more computation to train. GPT-4, the one that's getting people a little freaked out about starting to think, you know, is this really, you know, a human talking to me? Like sometimes people got freaked out earlier about GPT-4. Now we're up to 1.8 trillion parameters on 120 layers, 100,000 token dictionary, 100,000 token context, 13 trillion training tokens, and another 100 times more effort into training. Sam Altman is trying to raise like $7 trillion to train GPT-6. So, you know, I don't know how much compute that buys, but, you know, you see how these numbers are going up drastically each year or two. So when we talk about reducing complexity, so if you have a model of the size of these models doing this work for you, to give the answer up here at this layer, to give the answer in terms of transformers, is going to be about as complicated as giving a story about the talk that I just gave in terms of the movement of electrons, right? You just have this beyond massive complicated story because there are 1.8 trillion things going on up here. So to try to work through it, oh, how do we get from here to here? Nigh unto impossible, right? You got an enormous amount of data that you would try to have to work through to find, you know, it's just impractical. But yet I can still say at this layer, well, yeah, that's right. Why did it give the answer Mark? Well, because that's a picture of Mark. Why do I say that it's hallucinating? Because that's not a picture of Mark. You know, I can give stories about inputs and outputs at this, you know, human layer, this in the space of reasons that are really compact answers that I cannot give up here because these have to be a wildly complicated answer that no one knows how to give. That's what we call them black boxes, because no one knows how to explain through 1.8 trillion parameters what's happening. So at the same time, though, it seems clear that whatever's happening down here is just the product of this. After all, how did we train this thing? Well, by manipulating these parameters, right? So given that I trained it by tinkering around with this, it seems like this must be a result of this. So it's probably not going to be strong emergence, it's just going to be weak emergence. So I think that AI gives us evidence for non-reductive physicalism, for rejecting non-order determination, for saying that we have two good explanations here. They're both good, but we shouldn't get rid of either of them. We shouldn't get rid of the explanation in terms of hallucinations and reasons and rightness and wrongness and all that stuff, because that's the only explanation that we can give a lot of the time. At the same time, we don't want to get rid of that richer explanation at the lower level, because it helps me relate things. So if I want to know why was it wrong here, I might give an answer like she did. Well, the data was out of the context window. Like I gave it more than 100,000 tokens of data, and so when I asked it about it, it had forgotten, what I was asking about or something. So I don't want to get rid of this aspect of the story, because it's critical again to answering why things go wrong when they go wrong. In the same way that for a human being, we would want to give answers to the layer of reasons. Oh, he was lying to me. Oh, he forgot or whatever. But I also might want to give sometimes neurochemical answers, right? Why did he forget? Well, maybe there's some neurochemical story about which neurons were responsible for him remembering that or something like that. So that's the basic story. I want to say that AI is emergent in some important way. We have a lower level system that once you get complicated enough, you have to kind of find a new abstraction to describe it in, some new story that you want to tell that's simple enough to understand, simple enough to be a powerful explanation in a way that you can't give about the lower level, even though the lower level seems in a way well behaved and well understood according to this old 2017 paper. So AI should give us some evidence for non-reductive physicalism, that we have a system that we want to describe in narrative terms, ascribe genuine meaning to its words. After all, when we read those texts from AI, we think they mean something. We think they're right or wrong, whatever, even though we also want to tell a physicalist story about how we got those answers just in terms of the operation of computers. All right. Thank you, Mary. Questions? Go ahead.
So you said GPT-4 is about 1.8 trillion at 1.8 trillion parameters. My question is, did human beings put those parameters, or did the AI put those parameters by itself?
Well, so the way that the training works is basically you take text. So so you see the I don't know how many chalk, but okay. So you see how the training tokens. So you have 13 trillion training tokens, right? So those mean you have corpora, right? Like Wikipedia or whatever. So bodies of text. And what you do is thank you. See how So we give the AI something like a snippet of text where he is giving a lecture is our sentence. We blank out that last word, right? We say he is giving it. And we have to get to guess what word comes next. So some things wouldn't make sense, right? So some things like he is giving a fire engine. That's not a thing, like you're never going to see that in any English corpus. Like it's a thing you could make as a gift, technically, right? It's perfectly formed English, but there's probably no sentence in the wild that says he is giving a fire engine, right? But you could say he is giving a gift. That's kind of trivial or silly, but you could see it, right? But you could also see he is giving a lecture. So across all those corpora that you see in the wild, it's going to find certain words that are more and less common, right? And so it's going to train to try to predict the most common words. So I don't know where the relative frequencies are, but whatever it is from those texts that are out in the wild, it would learn to autocomplete this as saying there's, a 1% chance that he's giving a lecture. There's a 1% chance that he's giving a gift. There's, you know, a 5% chance that he's giving a hug. You know, whatever it is, right? And so that's what these parameters are. They're kind of like the stored memory of how to complete sentences. That's the idea. So it's trained by looking at all of these sentences in these real world texts from, you know, books and Wikipedia and whatever, to try to predict how those sentences go, what comes next. So that's where the parameters come from. They're kind of like a stored memory of how to predict what comes next.
You know, in the situations where it generates code,
Yeah.
does it use that predictive programming too? Does it use that predictive programming too? Like
What programming? Sorry.
predictive, like
Predictive. Yeah, exactly. That's right. Yeah, it does the same thing for generating code. So, these texts are not. Some of them are ordinary English texts like Wikipedia or whatever. Many of them are foreign language texts, or all the other languages of Wikipedia say. But many of them are also programming texts, right? So everything that's on GitHub, whatever, all of that code that's out there. And so, yeah, the same thing in programming, right? If you have for, then, you know, what's going to come next? Like, you know, while, or, you know, whatever, you know, if, like, whatever's going to come next in the code, yeah, it's predicting the same thing again. And obviously it has more context, like, well, you know, what's the headers on this file, or is this a Python file or a C++ file or whatever, and that's going to determine, you know, what idioms that it's going to use, because that's all kind of part of that context that it's working with. Yeah.
So these concepts of weak and strong emergence,
Yeah.
which I'm still trying to get my head
Sorry,
around.
a lot of philosophy jargon there.
No, but it's good. I'm like, this is the contribution, is these concepts. Is there anything in the discussion about those concepts? I'm thinking of the ethics of this stuff. So the potential for things to go wrong are higher in either, or is there any relationship between that typology and some kind of ethical framework or ethical concepts?
Like most things in philosophy, I'm going to say not that anyone agrees. So you may find out by now, if you get two philosophers in the room, you're always going to get two different answers. So partly because no one seems to agree on, well, first of all, so the way I like to think of it, and the way Jessica Wilson likes to think, so Jessica Wilson, she's a professor at the University of Toronto. Her 2121 book is kind of the current kind of Bible on emergence, you might say. And the way she and I think of it is that these are different things that we could say apply in different cases, right? So I might say, well, how does AI fit in this? Oh, I want to put AI down here, right, as being non-reductive physicalism, where there's, you know, overdetermination would both apply. And I might take other situations, other descriptions from the various sciences or whatever, and put them in different spots. So we're kind of flexible about the framework. It's not like there's one of these that's true all the time. It depends on what we're talking about. But that's not true. So there are many philosophers who would say, no, I deny distinctness. So I think physics is really all there is, and everything else is just fancy descriptions of physics. Boom. In every case, I'm going to give the same answer: deny for, be a reductionist, you know, boom. So if you're that kind of person, then first of all, you wouldn't even say that there's any case where this would apply. But second, in terms of the ethics, since you would think that human persons too are just physics, right? You've said that in every case we do for, we just deny distinctness. Human persons too are just physics arranged in the right way. You would have to take your ethical principles from somewhere else, right? Why is that arrangement special, or deserve special ethical care, such that we care about what happens to humans, not what happens to rocks? We have to come from somewhere else, right? Wherever that might be. It wouldn't really have anything with metaphysics, because we think the metaphysics is the same. So then Wilson actually does think that human free will is kind of the only example of strong emergence. He thinks there's no kind of analog in the natural world for that, and that everything else, so basically, you know, for Wilson, if we go back here, right, she wants to draw like a real, well, depending where you put free will in terms of psychology, but like a real hard line here, right? And say, here for biology and chemistry, we have weak emergence, but psychology, we have strong emergence because free will, she thinks, is the only thing that's strongly emergent. So if you take a view like hers, then you would say that there probably would be some ethical, implication there, right? Because, well, the things with free will are also the things that are moral agents and, that we care about. Now, I think that much of my research is about the principle actually that chemistry is strongly emergent. With respect to physics, that's not a popular view, but it's my view. So I again would have to say that that wouldn't be creating a moral status because, I don't think, methane has moral status just because it's strongly emergent. So, so I think there's not like a general position there. So in Wilson's view, particularly, there would be some connection, but I don't think there would be a general connection between the ethics and the metaphysics there. There might be a view that you might say something like, if the metaphysics and ethics are connected, then you would need at least weak emergence to have any kind of ethical standpoint, because it's weak emergence that sort of like would give you the idea of a hierarchy in the first place, right? It's weak emergence that would tell you we genuinely got something new going on here, whether it's because it's a totally novel power or even just because we have like a simpler level of description, but still that's somehow new, at least in that way. That would be a kind of a precondition for ethics, if there was a connection at all between the ethics. But sorry, that's a typical weak philosopher's answer. I apologize for that, but it's the state of the field.
If we assume that AI is weakly emergent, then where do we look to for ethics?
I mean, yeah, so you might have to go to some other principles. So one answer that's gaining some popularity in philosophy literature is agency. So does it have somehow interests, and perhaps can it be harmed? A lot of people think that what gives us moral status is that we have interests that can be harmed, and that's nice as a view because it could also encompass why animals might have some moral status. Even if they have fewer interests, surely they do have some interests, not living in pain or whatever, and that gives us some reason to treat them in a certain way, which we might think is a benefit of a moral view. So you might look there, but that's perhaps related to emergence. But you might have to say emergence of what? Like agency itself might be something that would have to emerge. It would have to be either some way of summarizing lower level things, like as I've described in this talk, that that we want to give maybe an answer in terms of like semantics to give a higher level story here, that what's emerging is semantics, that Mark means this guy, so if I'm describing a situation where you have semantic emergence, you might think that agency is another thing that could emerge, that a certain description of a bunch of lower level stuff might be, well, it's acting for interests that can be harmed or something like that. But they wouldn't necessarily go together, right? Something could have emergence of a certain quality or property, and that wouldn't necessarily tell you whether it emerges another quality or property. So that's one thing that people would look at is the question of, I'm not saying every philosopher would agree with this, but those who are thinking in this direction might focus on agency and ask less about weak or strong emergence, though some might say agency requires strong emergence or whatever, because they would say it's so different than, that physical things can't have interests, it's got to be totally novel. So some people disagree about what agency is, but the question would be less about does agency emerge weakly or strongly, and more does agency emerge? Yeah. Oh, sorry. Sorry, just a new question. Okay.
Oh,
I have like off-topic question.
So I still don't have a clear understanding of emergence.
Sorry, that's my fault.
Okay. But are you like for something like free will, is it strong emergence because there's really not a definitive answer on if we do have free will or not?
It's not really a definitive answer. Just the question of, so the idea of weak emergence is you have something that in a way could be predicated of the more complicated layer. But it's just so complicated that we don't really have any way of tracing it through or way of showing that it is. So there's a whole research program that maybe the concept people are more familiar with called explainable AI, which tries to say, go into these particular parameters and say, well, what do they mean? Tries to push the semantics down into this layer. And if that succeeded, if you could figure out of these parameters, you know, what do they mean? If you then you would say, well, this wouldn't be weakly emergent anymore, right? No, we could attribute semantics genuinely at the lower level. And so there's no kind of new description that we're having at the higher level. It's just a kind of a sum. But if in weak emergence, what we see is there's a kind of a simple summary that doesn't exist at the lower level. So we would say that somehow it's got to be true that in here we're identifying the picture as Mark, but we just don't know how that works. Here we give a simple summary of that at the higher level. In strong emergence, the idea is that you have something totally new, that somehow what's going on at the higher level is just not explained by the lower level. So the idea would be that for Jessica Wilson, she would say that free will is not explained by anything in physics or chemistry or biology. This is something totally new that's only true of human persons and it's not explained by any lower level. So that would be an example on her view of strong emergence, but you can believe in strong emergence without having her view. You can think there are other things that are strongly emergent, or you can deny that free will is strongly emergent or whatever. But it's not to do with whether we can understand free will, but rather to do with whether it's somehow connected to what's going on at the lower level or whether it's something totally new at the higher level. So weak emergence, we have a kind of simpler way of understanding it, but it's still connected. Strong emergence, the levels are connected. We're not a dualist. There's not like a new reality, but it's got this kind of new attribute, new power, we might say, new ability, which is just not connected in a way to what's going on at the lower level. That's the difference. Does that help?
Yeah, so it's kind of like strong emergence. There's really no understanding of the foundation, the things that led up to that emergence.
Well, it's not really so much no understanding. They deny that there could be any understanding, right? Because if this is genuinely novel, then the claim is not just that we don't understand it, but that there is no story that you could give about, like you could give a certain story in preconditions. You could say, well, if this didn't happen, then this wouldn't happen. Like, but you can't give a kind of sufficient condition. You would never be able to say, well, when these are arranged just like so, when the protons and electrons are arranged just like this, that's a human exercising free will. You could never give that kind of sufficient condition because this is a totally novel power. That's the idea.
One more question. I just had a question. Like, when do you think, in general, if you just guess the timeline, like, when do you think we'd get to human level intelligence? If it's possible, with like just taking past data and just like extrapolating.
It really depends so much what that's supposed to mean. I mean, humans do so many different things. And human intelligence is not necessarily like a well-defined, narrow concept, right? So, so one thing that humans tend to do well is like empathize and react to other people. And that's actually part of what we say, right? So even for an LLM thinking of prompt and response, part of the way we respond is based on our sense of how the other person's feeling and what we can do to kind of manage their feelings, right? To calm them if they're anxious or whatever the case may be. And a lot of that happens at a layer that's not even kind of mediated by the text, right? So, we even like exchange pheromones or something like that, right? And that helps me to know whether you're anxious. And then, at a subconscious level, and then that's going to help me modulate your anxiety. Is that part of intelligence? Well, if so, I don't know how GPT is going to get there because it doesn't have a pheromone receptor, right? There might be other things that require a kind of sense of agency or planning. So, one thing that language models struggle with is the question of, for ethics, it's given current ways of training them, it's kind of impossible for them to have what we call a deontological ethics, or an ethics that takes certain principles as like inviolable. And they tend to have like a kind of a consequentialist view that, well, it depends how much else is going on. And that's partly just in terms of training. So a little aside with people who know about training, if you think about how gradient descent works, right? Like the question of, you know, how much reward I get for being down here in the gradient, it's always finite, right? And so because it's always finite, you could always, in theory, you know, have a deeper one somewhere else, and I could be in a local minimum. And I could really want to be down here, right? That's at least theoretically possible. Whereas the idea of a deontological ethics would be, say, for Kant, that there's no situation in which you could kill someone else intentionally. That's just like right out. Like there's no situation which we could ever justify that. So that would be to say that somehow there's never any deeper place I could go to that would take me over to that response. But the very way that LLMs are trained doesn't seem to allow for that kind of ethics. So if part of human intelligence is principles like that, then we might need a whole different model than we have now, and no greater size will work. If, on the other hand, we just mean in terms of, you know, doing the kind of things that we take as human intelligence tasks, then I would say we're already there. I mean, as I said, that, you know, this can pack 90% on the bar exam. And not just the bar exam, because maybe you think, well, law has a lot to do with words, but it's also passed the architectural licensing exam, which involves a lot of images and reasoning about spatial relationships and stuff like that. So you might just think, well, if you can pass the architectural licensing exam, then you're intelligent. Like, just, you know, go home or die. So it really depends a lot on what you mean by that, and it's not at all clear what we should mean by that. It also might be the case that if some people think, like say David Chalmers down the street at NYU thinks that human intelligence is strongly emergent, and if you accept my argument that LLMs are weakly emergent, then you might think that no amount of this will ever get you this, right? So you might get a kind of strong mimic of it, but you'll never really have it because this is actually has some kind of deep power of novelty that's not present here, even if this could kind of perfectly mimic it. That's another view. So it just depends what you mean, and I don't have a better answer than that.
All right, thank you very much for having me. Okay, grab a sandwich.